I would like to introduce our prestigious guests, Dr. Mark Henderson and Professor Stephen Cowley. Mark is on the right.
Your left.
Having grown up all over the United States, at age 14, Mark learned about nuclear fusion and decided he would dedicate his career to making it happen. He received a PhD in physics associated with the design, construction, and operation of a stellarator at Auburn University. Hopefully now you'll know what a stellarator is. From there he went to Lausanne in Switzerland to develop and perform experiments with a microwave heating system on the TCD Tokamak. After 16 years, he headed to the south of France to work on the ITER Tokamak, in charge of the microwave system. Mark's dream job is either to do what he is doing now, or to direct a science museum and pass on his passion for physics and fusion. When he is not doing physics, he can usually be found outside, either working in his garden or just enjoying the nature around him. Our second guest is Professor Stephen Cowley, who is the 31st president of Corpus Christi College. He is the first scientist to hold the post and has had a lifelong interest in realizing fusion power. After reading physics at Corpus Christi, Steve became a graduate student in astrophysical sciences at Princeton University, studying the theory of fusion plasmas. He was later awarded a fellowship from Princeton University, where he stayed before returning to the UK. Here he worked at the United Kingdom Atomic Energy Authority, or UKAEA's, Cullen Lab, and taught at Corpus. He also taught physics at Princeton, UCLA, and Imperial College. In 2008, he became the director of the UKAEA's Cullen Lab, and from 2009 to 2016, the chief executive officer of the UKAEA. He is an author of over 170 refereed articles, and has even presented a TED Talk on fusion. In 2014, he was made a Fellow of the Royal Society and the Royal Academy of Engineering, and since 2011 he has been a member of the Prime Minister's Council of Science and Technology. His research interests outside of fusion include the origin of magnetic fields in the universe and explosive events in astrophysical and laboratory plasmas. So into the discussion. I've always felt that if people knew more about fusion, then they would understand why I and scientists everywhere think we need to invest in it so much. They would also feel immeasurably safer and more excited about the prospect, as I hope you do after watching that film. If the public could feel more enthusiastic about it, then maybe governments would be even more active about investing in fusion research. There was a point made at the end of the film about investment in the research and development of fusion being critical to its success, but lacking thus far. Which brings me to my first question to our guests. Do you think that the funding available to fusion is sufficient for its success? And if not, where do you hope it can come from in the future? Over to you guys.
I'll let you answer first.
I thought we agreed that you would be the first.
Do we agree on that?
Yeah. It's clear that if we spent more money, we would move faster. But it's how you spend that money. There was some talk in the film about, having a diversified set of ideas. And this is what's really difficult, because we're at the point with the ITER project where we can make a machine that can do fusion. I'm pretty convinced that ITER will actually produce what we call a burning plasma, which is where a plasma produces enough fusion to keep itself hot. And then it's hot enough to produce more fusion, and more fusion keeps it hot, so it's self-sustaining fusion burn. But I'm not convinced yet that we have all the ideas we need to actually make fusion commercially possible. And what I think we need to think very hard about is what is it that will actually fit into the market? What kind of electricity producing fusion device can we actually sell to the market in the future? Because we've got to get to that in the end. It's not sufficient just to demonstrate that we can do fusion. It wasn't sufficient for the Wright brothers to fly around in a circle or a figure of eight. You've got to change that into actually commercial fusion. And so I certainly think we should have more funding. There was a point made in the movie about the cost. Sort of about between 1 and 2 billion a year is being spent on fusion, a huge amount now by China. The world energy market is 7 trillion a year. And we spend about 2% of that on energy research. If you go to any of the big high-tech companies, they wouldn't be alive if they spent that little on research. The future of energy supply is an existential issue for humans. To be spending only 2% of the world's market on research in all kinds of energy is ridiculous. We should be spending 8 to 10%. And 8-10% of 7 trillion is a lot. And it's an awful lot more than we're doing now. And I think that on that scale, one would expect fusion research to go up by factors of 3, 4, 5, if you were spending the right amount of money on all kinds of energy research.
I tend to agree with everything you said. I would add...
we're supposed to disagree sometimes.
No, we're supposed to disagree? No, but ITER is there, as the title of ITER, really ITER is an experimental reactor. And it's there for us to learn how this concept of a burning plasma actually works. And so it's an educational device. It's not to produce the next reactor. And we need this to understand, along with other devices, for example, MAST, that's in Cowley, England, right nearby. The other thing is about money. One of the things when I was a kid that pushed me towards science was the Apollo projects. And when I was a child, I was watching the first man landing on the moon, and that was Neil Armstrong. And there was 2 people who set foot on the moon. There was Neil Armstrong and Buzz Aldrin. And there was a third guy who was up in the command module. And to put those 3 guys on the moon, it cost, in today's dollars, about $120 billion, which is significant compared to what we need to achieve fusion. And, as a kid, seeing this happening, I was fascinated. Also, I was fascinated because the guy who was up in the command module, the guy's named Michael Collins, he was my dad's roommate in college. And so for me, there was a direct connection to see that a common person, someone who's just a normal person, could do something big. But when a nation was behind pushing something and investing the time and the money, and where there's a will, we could do a fantastic thing. In putting man on the moon, 120 billion, we did something fantastic. And I think for fusion, that's what we need. And not just because we're fusion scientists, we push this, but I sincerely believe we need fusion to be able to survive as a species, because we need something as a clean alternative energy. And you can look in the Pacific right now and the amount of plastics that we're dumping into the ocean. You can look at the CO2 levels, everything we're doing, we're basically like the yeast, we're killing ourselves off by our own pollution. And I think fusion is a path to avoid that. I'm not sure if that answered directly your question, though. And I don't think we disagreed.
Thank you. My next question. Many young people involved in science and politics are interested in solving the challenges of climate change. What do you believe are the biggest challenges we face in this area?
Can I take a stab? I think one of the things is just short-sightedness. I think that we all, as in the beginning of the film, we all take an easy path. And it's very easy for us to find an energy source that is easy to live off of. We don't worry about the consequences. We don't worry about the pollution. And I think what we have to do as a species is learn that just not extracting the coal, but the byproducts, the CO2 and the pollution, is something that's going to affect us. And I think the new generation is going to have to learn not to make the mistakes the old generation made.
When I first started thinking about working in energy, we all thought that fossil fuels were going to run out quite quickly. And actually that probably would have been a good thing, because fossil fuels are not going to run out quite quickly, because we've invented ways to extract more and more hydrocarbons from more and more difficult places, so that with fracked gas and things like this, we've got several hundred more years of fossil fuel production before we run out of them. The problem with that is that if we burn that much fossil fuel, we're going to severely damage the climate and the environment. And coming to a political consensus that says, we won't do that when it's cheap, easy, and just what Mark was saying, all these techniques to extract fossil fuels, gas is pretty much, dirt cheap in America. No point in insulating your house when you can burn all the gas you like and, leave the windows open. This is an enormous challenge, because it means that we have to get together for the common good and do things that are against our economic interest. And I think that's going to be very, very hard to do. And it was said that, not only does fusion have to be able to produce energy, it has to produce energy at a price that's competitive, that will stop us burning fossil fuels. And that's really very hard. This is, again, the challenge for solar. It's the challenge for all the renewables, which is, it's just very easy to just put pipes in the ground and blow up bits of rock and frack gas and do that. So we have two choices. We have two ways out of this problem, and one of them is the political way, which I think, if we look at the Paris Accord and we look at the various ways in which we've tried to regulate climate change, they've largely been impotent. We've really not got way. That's the political way to do something about it. I think the only other way is an economic way, where we innovate our way to a point at which other energy sources are just cheaper and we'll use them. Cheaper, or at least competitive.
Thank you. There are plenty of technological developments to be made for fusion power to be a reality. Outside of science and technology, what other areas do you think will require development to make fusion a success in the coming years?
We'll give it back to you. No.
So we're doing a double.
Exactly.
I think there's obviously, we've been talking about funding and people focusing on this energy problem. There's an awful lot of technologies that would help fusion. I know you work on materials. We need materials for fusion reactors that we don't really have. Because when you build a fusion reactor, you've got fusion going, but fusion creates neutrons, and neutrons cause material to decay. To get, the neutron bumps into a nucleus inside the material. That nucleus recoils, it causes a little melt spot in the material, and the material eventually loses strength. So we've got to solve the problem of resilient materials. If we could make magnetic fields that are much stronger, that would be helpful. That would be enormously helpful, because we're limited in the size of the devices that we have by the need to keep the heat in for about 3 seconds. We can do about 1 second on jet just down the road, but we need about 3 seconds. And to do that, either you make the device bigger so it takes longer for the heat to get out, or you put on a stronger magnetic field which calms down the bubbling turbulence that causes the heat to get out. If you could figure out a way to make a magnetic bottle that was better than the Tokamak, then you probably could make smaller, cheaper devices. So I'm not answering your question. I'm saying I think there's room for a huge amount of technological and scientific innovation here. And somebody's going to have some bright ideas that we don't have at the moment. And maybe it'll be some of the people in the audience.
I'm going to be a little bit radical, because I think where there's a will, there's a way, and I think the technology will come as we explore. I think what we really miss today in order to move forward is, one is communication. I mean, just the fact that if this was seawater, this would be equivalent to 350 liters of gasoline in terms of energy content. and you look at the size of the ocean, I mean, the energy potential is just, it goes on not just for hundreds of generations, but thousands and hundreds of thousands of generations. So the energy is there at our fingertips. But I think it requires one, communication to drive, to understand the potential. And the other one, I think it's what Steve was saying, I think we need to change our mentality. We need to go toward realizing we can't continue at the rate that we're moving. We need to have a change in mentality that the acts that we're doing will leave pollution, will leave a very long-term impact on the earth, and we are all guilty of that. And we all have to make a conscious decision to stop, either through technology, either through innovative solutions, or just through our own personal willpower to conserve energy, stop plastics, try to push forward in the energy source. And so I think it's our choice to move or our choice to pollute the earth. And I think truthfully, we're all lazy and we're just polluting the earth. So I think that's outside of technology. I think it's a change. What we require is a mindset, a mind change.
Yeah.
And I think it's impossible.
Hopefully, better communication through films such as this and people like you going around talking to the public about it will help. Might take some questions from the audience now. So,
You just pick, yeah.
Can you hear us okay without a microphone? Is that okay?
I can talk loud. I have a question for a particular teacher, which is how much of a sad experiment it is, because I've read many times, for example, satellites, while they're building them, the technology that actually goes out of space is actually not that new when it's actually operating. How much of ITER can be changed and adapted as we learn more about fusion?
Well, I mean, obviously you fix the design at some point and you pretty much have to go with that, and if you don't, you get into all kinds of trouble. So there are quite a few elements of the ITER design that probably we would do differently now, because it was designed, over 10 years ago, more like 15 years ago. And we've learnt things since then. This is, as you say, like with satellites, you can't get around that.
Yeah.
And this is the advantage of building small things, that you build fast. You evolve very quickly, and it would be nice if you could do fusion in the garage in Palo Alto, but it doesn't seem that you can, or even a storage facility in Middlesex, New Jersey.
I'm not sure if the microphone works, so.
okay, do you want to start?
It does work?
Is it working?
Who was
It's just this gentleman.
So on sort of point of doing sort of fusion in the garage in Palo Alto, so how sorted are that's physical modelling of the I mean, that's sort of this incredible engineering challenges to solve, but if we had, like sort of how if we had a sort of simulation of sort of design, would we be sure it worked without building it?
So it's very. Sorry, I'm going to answer that since I'm a theoretician. We are just about getting to the point where we can calculate the things that go on inside tokamaks. The problem is that tokamaks are turbulent, like pretty much, and the plasma inside a tokamak is bubbling away. And it has these little turbulent eddies that are about a centimetre across, and these carry the heat from the middle to the outside. And this turbulence is fiendishly complicated from a physicist's point of view, because it's a turbulence of a plasma which has electricity and magnetic fields in it, and has particles moving, or charged particles moving around. It's not the turbulence of water. The turbulence of water is still, a really difficult problem. The turbulence of plasma is very, very difficult. And only through really large high-performance computing have we been able to model that effectively. And even now, we're kind of okay at modeling what we see, but very bad at predicting what's next, which is not a good advertisement for the science yet. But I hope that we're going to get to this stage where our capability to model it gets to the point that we can do design in silico, which is what you're talking about, which is, use computers to design better things, iterate on that until we've got something that we really think we want to cut metal on, and then cut metal. Many of the people who've designed fusion concepts, including general fusion, they do a calculation at the beginning and then it behaves nothing like that afterwards. But I think we're getting to the stage that our science might be catching up, and we can do kind of design on the computer. I hope.
Yes.
If you take ITER, for instance, sorry, get me started. If you take ITER, for instance, ITER, the biggest machine in the world is JET, which is about 15 miles from here at Cowley. And JET has done 16 megawatts of fusion power. So, and central temperatures on JET can regularly reach about 250 million degrees. So the temperatures you need in ITER have been achieved. ITER is simply JET times 2. It's the same shape. The only difference is it uses superconducting coils instead of copper coils, but the actual plasma is pretty much the same thing. And that's how we know, roughly, how ITER is going to perform, because we know how JET performs and we know how to scale it from JET to ITER. So we didn't have to do a supercomputer calculation to do that. But it means that ITER is no more innovative than JET was. Right? And JET was conceived in before 1980.
Thank you.
So, is this working? Yeah.
It is.
So I want to go back to the kind of the guys in the garages in Palo Alto. There's not guys in garages now. There's spin-outs from MIT, there's spin-outs from Oxford here that are marketing themselves as small and nimble kind of companies that can do things that ITER can't do, because ITER moves like a tanker, and these companies can reinvent themselves kind of on a dime thing. Are they the future of fusion, or are they essentially a Ponzi scheme that's going to turn out that they're cold fusion in disguise? Because there's big money going into them, and there's going to be some disappointed investors if they're not the real deal. I'd like to hear what Mark has to say, because I sort of know what Steve has to say.
I was hoping to push this one off again on Steve. Now, a lot of those, like, Focus Fusion, I think some of the things that he's tested were tested back in the 60s and 70s. There is a place in San Diego is also, I've lost the name of it. Tri-alpha, a reverse field configuration. Those things have been also tried. Those are many orders of magnitude behind what we're achieving in JET. What we're achieving in ITER. So some of those they have a new twist, and they could potentially provide something that will be highly performant. But a lot of those we've already tried, and they have not been successful. One thing I like about general fusion is that they're kind of making a combination of inertial confinement and magnetic confinement, so it's kind of a new domain. And there's a potential. It's extremely challenging, like he said, but there is a potential. And if there is a potential, I think it's something that we should invest in. I agree on everything that's been said about ITER. It's very complex, it's very enormous, it's massive, it's expensive. I think it allows us to move the step forward to be able to understand a burning plasma. But these other smaller machines, I think it is worthwhile to invest in them, but to do it in a coherent, logical way, where we're investing in ones that we think are going to be successful in combination with what we're doing on ITER. A lot of the spin-offs, I think, are just, they think, we can get fusion in 5 years, and it's now been 5 years, and they're nowhere near. just because they have the same enthusiasm, and yet they don't really understand the challenges. Where magnetic confusion has now 50, 60 years behind us. And one thing that sorry to talk too much, one thing that we fail to understand is the way that we progress or we measure our progress is by measuring the density, the temperature, and the confinement time. And from the 1970s to the year 2000, if you plotted how well we were doing and progressing in higher temperatures, higher densities, and higher confinement times, we were exceeding that of the chip technology. So if you know Moore's law, which says basically the density of chips doubles every 2 years, we were doubling our parameters on an average of about 1.5 years. And so we don't see that. You don't see that as a person in the public, because we need to get to the point where you're actually making energy. And we're not going to make that until after ITER. You see Moore's law every day because the iPhone that you just bought last year is now out of date because the technology has improved. And small steps in technology and chips is a huge benefit commercially. Fusion, we've been making these progresses. We've been exceeding that. It's just now we need a bigger machine. And it costs money.
You never want... When cold fusion came out, I was a postdoc at Princeton, and it was immediately obvious that there was something really fishy happening, because they were claiming not only fusion, they were claiming fusion without neutrons. They were, in fact, what happened on the day that cold fusion came out is that it was announced not in a scientific paper, it was announced in a press release. And my wife was working for the nightly news on ABC in New York, and she called me at Princeton, and she said, "You're out of a job." She was laughing, which I'm not quite sure why she was laughing, actually, but because we were going to be short of money. But I immediately tried to find out what was going on, because it was a press release. You couldn't tell what science was going on. So I called a friend, actually, who I did physics at Oxford with, who was the then science correspondent of the London Times, and said, "Do you know what's going on?" And he said, "No, but I have the home number of Martin Fleischmann." There were two guys claiming cold fusion, Fleischmann and Pons. And so he said, "I'll give you the home number." So I called Martin Fleischmann, and this was sort of midday in Princeton, so it was about tea time in Southampton. And I said, "Professor Fleischmann, I'm calling from Princeton, and I'd love to hear about your experiments, because it's just been announced, and you've done fusion." And he said, "Yeah, we've done kilowatts of fusion power coming out of this little electrochemical cell." And I said, "Kilowatts of fusion? Well, Professor Fleischmann, where were you standing when kilowatts of fusion was happening in that cell?" And he knew what I was asking, and he said, "The funny thing there was no neutrons coming out of that reaction." And once he said that, you knew immediately that there was something really fishy about this experiment. To change, this is an electrochemical cell, so the actual physics of the electrochemistry is really hard, and I was confused by it. But that once the nuclei get together in a fusion reaction, it's about nuclear physics. And all this fancy stuff around it, the nuclear physics is going to be the same inside an electrochemical cell or anywhere else, right? And we know a lot about the nuclear physics of fusion reactions, and these ones produce neutrons. So he didn't have any neutrons at that point. And this has been, in some sense, the promise of fusion is fantastic. And sometime you think there might be a breakthrough, and there might be a breakthrough in which you suddenly break through, and there's this idea that nobody had before that totally revolutionizes it. But you've got to be very careful that you know enough physics that you're not confused, right? And they were, in the end, a laughingstock, because they didn't spend the time to look at the experiment, make a few calculations, ask themselves why there are no neutrons coming out of this experiment at that time. Now, that kind of thing happens in roughly about half the fusion startups. The other half are doing really legitimate research. but they're just way behind the parameters that you get in the big government-funded projects. The temperature in the best of the startups is this tri-offer. They have reached about, what's a kilovolt? It's about 10 million degrees. They have had funding which is best part of $2 billion to get there. That's about the cost of jet. Jet has got 25 kilovolts, so 25 times as much temperature in the center. The density is about 5 times their density. So the parameters are so much closer to fusion, and at this point we're learning nothing from that $2 billion of venture capital investment, which included a lot of money from Paul Allen, one of the starters of Microsoft. But maybe we will in the next round.
Okay, we've got time for one more question. We go back there.
So the timescales for ITER are long. The comparisons to cathedrals are pretty apt. And especially if we won't have like full DT plasma until 2035, I think. Global warming, on the other hand, which was been mentioned several times as like a reason for pursuing fusion as a power source, is essentially upon us. Like we already see record temperatures every year. Disregarding the potential for some disruptive small startup to achieve fusion much faster, do you still think that, given that global warming, you could argue that global warming is becoming worse at a rate faster than ITER is getting built, then do you think that the ITER and Eurofusion roadmap is still relevant for fighting climate change?
I can do that quick. Yes. I think you have to have a two-pronged approach, or come at from two fronts. We need to have a short-term solution, and fusion is going to be the long-term solution. Because, ITER is going to have, right now, scheduled first DT operation 2035, as you stated. We will learn from that, and then you will have to build the first commercial reactor, which is going to take time as well. So the first commercial reactor is even further down the road. So we do need to find a way to stop producing greenhouse gases, and that we do whatever we can to do that. But the long term is rely upon fusion, and that may be in 50, 75, 100 years. But then from that point onwards, it's going to be a fusion economy. And that means not just 100 years, 200 years, 1,000 years, 10,000 years, but fusion will go on for hundreds of thousands. And so I think we have to have two solutions, short term and long term, and the long term is fusion.
Yeah, I guess my answer is somewhat similar. Giving talks about this and working with government, I see the problem we have. We can ameliorate with what I would call transitional technologies. These are technologies that we can use and have no CO2 output, have no greenhouse gas output, such as nuclear fission, such as carbon capture and storage, that only really we can do for a few decades. So you take carbon capture and storage. You need to store about 40 gigatons of CO2 a year. And it's believed that possible places that we can put that, we can store roughly a teraton. Right? So it's about 20 years worth of CO2 output before we sort of run out of oil wells to stuff the CO2 into and things like that. So those are technologies that buy us time. And conventional nuclear fission will do the same thing. And backing up a lot of use of wind and a lot of use of solar, we might be able to stave off serious global warming for several decades, maybe a whole century. But after that, we have to go to truly sustainable solutions. And we won't be doing thousands of years of fission, and we certainly won't be doing thousands of years of carbon capture and storage. And so those transitional technologies will carry us through this sticky time and then get to that. But I don't know if there's the political will to do that.
I'd like to thank my speakers very much. Thank you all for coming today. I hope you enjoyed the film.
Thank you.